third and final section of chapter 3 on kinematics, and this section is on acceleration varying with velocity. So in these types of questions, the acceleration is a function of velocity. Now we can use a equals dv dt, and we use this form here when we have a question where time is involved. And when we want to find distances, we'll use the form a equals v dv dx. Now often in these questions you'll find that when you do the integration part, you'll need to separate the variables, use the separation of variables, so that you would have like all your t terms on one side, your v terms on the other side, for example, and then you'd integrate both sides. For example, if you're using this, you'd integrate one side with respect to t, so that would be over this side, and then whatever you have with your v terms over this side, you'd integrate this with respect to v. And of course, don't forget your constants of integration. Example 12. A van moves along a straight horizontal road. At time t seconds, where t is greater than or equal to 0, the acceleration of the van is 625 minus v squared all over 200 meters per second squared, where v meters per second is the velocity of the van. The van starts from rest. Part A, what we need to do is to find v in terms of t. Since acceleration varies with velocity and we're looking for a time element here, we use a is equal to dv dt. A is 625 minus v squared over 200 equals dv dt. And the way we're going to solve this is by using separation of variables. So I'll multiply both sides by dt and divide both sides by 625 minus v squared. So that will give me 1 over 200 dt is equal to 1 over 625 minus v squared dv. I'm going to integrate both sides, so let's stick an integration symbol there. The left hand side is straightforward because that will just become 1 over 200t, or t over 200. For the right hand side, we're going to have to use partial fractions to integrate this. So first thing we'll do is we'll say that the denominator is the difference of two squares, so 25 plus v, 25 minus v, and as partial fractions we're going to have a over 25 plus v plus b over 25 minus v. So from there we're going to have 1 is equal to 25 let's get this right here, a times by 25 minus v plus b times by 25 plus v. Right, so let's start by making v equal to 25. When v is 25, this is gone, so you're left with 1 is equal to 50b. So that means that b is 1 over 50. Then we'll make v equal to negative 25, which means that this will disappear. So you'll have 25 minus negative 25. So we'll have 1 is equal to 50a, which means that a is equal to 1 over 50. So this integral here can be written as, now you've got 1 over 50, and I don't really want to be writing 1 over 50 here and 1 over 50 here. I'll take it out as a factor. So I'll have 1 over 50 and stick it on the other side of the integral sign, 1 over 25 plus v plus 1 over 25 minus v. So now we've got it in a form that's going to be much easier to integrate. So this is still the right hand side, so I'll have 1 over 50 and then a natural log of, because the top is the bottom differentiated, 25 plus v differentiated gives us 1. And then for the second one, the bottom differentiated is going to give me minus 1 So actually it becomes negative log 25 minus v. That minus ensures that I end up with a positive 1 at the top here. Putting my right hand side and left hand side together, I have 1 over 200t is equal to 1 over 50. Now I'm going to put the logs together because I've got the log of something minus the log of something. So I can write that as a single log, which means I don't need brackets anymore. So natural log 25 plus v divided by 25 minus v, and not forgetting my constant of integration plus c. And also making sure my t is in the right place. It makes it look like it's 200. The t is at the bottom. Next I'm going to times both sides by 50. So I'll get 50 over 200, which is a quarter. So quarter t is equal to log 25 plus v over 25 minus v. And now what we want to do is to find our constant of integration. And we use this bit of information. The van starts from rest. So that means that when t is 0, v is equal to 0. When I substitute those values in, a quarter t on the left hand side just becomes 0. Then I've got the log, natural log, of 25 plus 0 over 25 minus 0. That's a log of 25 over 25, or the natural log of 1 plus c. Now the natural log of 1 is 0, which means that c is equal to 0. So the last part of what I need to do is put in my constant of integration. A quarter t is equal to the natural log of 25 plus v over 25 minus v, and make v the subject of this. So what we'll do e to both sides. So we'll have e to the power of a quarter t is equal to e to the natural log of that just becomes 25 plus v over 25 minus v. We'll times both sides by 25 minus v, like this. 25 minus t times by e to the quarter t is equal to 25 plus v. We'll expand the brackets on the left hand side, so I'll have 25 e to the quarter t minus v e to the quarter t is equal to 25 plus v. Let's just create a little bit of space. Then what we'll do is collect up all the v terms on one side, so I'll have v plus v e to the quarter t is equal to 25 e to the quarter t minus 25. Bring that over. Then factorising both sides, we have v 1 plus e to a quarter t is equal to 25 e to the quarter t minus 1, and then that leaves us with v is equal to 25 e to a quarter t minus 1 over 1 plus e to the quarter t. Then we can move on to part B, and part B says show that the speed of the van cannot exceed 25 meters per second. Now anytime you get something that hits a final speed or doesn't exceed anything, is increasing to a point where it hits this speed here, it's given a special name, and it can be called the terminal velocity. So you may get a question that asks what is the terminal velocity, or terminal speed, or the limiting velocity or limiting speed. So if you see those phrases, basically it's asking the same question. What can it not exceed? What's it basically tending to? Now I'm going to explain it this way. There's different ways of explaining it. So I said for any value of t, this expression here, you notice that you've got e to the quarter t at the top and the bottom. 1 is take away 1, 1 is add 1. So the numerator will be less than the denominator. And actually, as t increases, these two values are going to be very close to each other. And whenever you've got two values that are very, very close to each other, you've got a value that's close to 1. But because this is always going to be a little bit smaller than the bottom, that means that the whole expression is always going to be less than 1. It's going to get closer and closer to 1, but it's going to be less than 1. Now, v cannot exceed 25 because you've got this thing here that's getting closer and closer to 1, but always less than 1, and you're multiplying it by 25. And 25 multiplied by any value that's close to 1, yet smaller than 1, will always be slightly less than 25. So that's my way of explaining it. But as I said, there are different ways. Try and think of a way of maybe putting what you see here into words. Example 13. A particle P moves in a straight line. When the velocity of the particle is v meters per second, the acceleration of the particle is given by a equals 4v meters per second squared. Find the distance moved by P as the velocity increases from 10 meters per second to 15 meters per second. Now this is a question that involves distance. The acceleration is given as a function of the velocity. So that means we need to use this expression here, or this formula. A is equal to v dv dx. A is equal to 4v. Substituting that into the formula, we have 4v is equal to v dv dx. We can divide both sides by v, giving us 4 is equal to dv dx. We need to solve this first order differential equation, so we'll separate out the variables. So we'll have 4 dv dx, or 4 dx equals 1 dv, and then we integrate both sides. If we integrate the left hand side, we're going to get 4x, and if we integrate the right hand side, we're going to get v plus our constant of integration. So to find this constant of integration, we need a value of v and a value of x. Now we're not told explicitly in this question, but it does say that the velocity increases from 10 to 15. Now I don't know at what displacement the velocity was 15, but I'm going to call the displacement when it was moving at 10 meters per second, which is at the start of this question, x equals 0. So at the start, when x equals 0, v was equal to 10. So we'll substitute those in, and we'll have 4 times 0 is equal to 10 plus c, which means my constant of integration is equal to minus 10. So that will now give me a final expression as 4x is equal to v minus 10. Now if I'd put my constant of integration somewhere else, or I'd separated the variable slightly differently, I may get a different value for c. However, we will still get the same final solution. So if I rearrange it for v, I have v is equal to 4x plus 10. So now we can put in the velocity of 15 and get what the displacement is. We remember we put the displacement here as 0, so whatever we get here, that is going to be the distance moved. So we have a velocity of 15, 4x plus 10, just rearrange that to find x. So take away 10 from both sides, so we got 4x equals 5, and x is going to equal 5 over 4, which I believe is 1.25, and that's going to be 1.25 meters. Now we know this is the displacement because, as I said, we took this point when the velocity was 10 as a distance of 0. So anything after that is going to be our final answer. We don't need to subtract this from anything or add it to anything. Example 14. A particle P moves along the x-axis. At time t seconds, the acceleration of the particle is negative k squared plus v squared. where v meters per second is the velocity of the particle and k is a positive constant. When t equals 0, p is at the origin and v is equal to capital letter U, big U. The particle comes to rest at the point A. Find in terms of k and u, part A, we want to find the distance OA. So I see first of all the acceleration is given as a function of v. I've been asked for a distance, so we use A is equal to v dv dx. We have A equal to negative k squared plus v squared. So we put negative k squared plus v squared is equal to v dv dx. We're going to separate out the variables. So there is no x term, so actually we'll just have 1 left when we times both sides by dx. And then on the other side, we'll keep the v where it is and we'll divide both sides by the k squared plus v squared. Now I know there's a negative there, so to keep things a little bit more straightforward, let's put the negative over here and keep the negative on that side, and then we can add the dv like this. Now we can integrate both sides. Well, the left hand side is going to be nice and easy. That'll just be negative x. Then on the other side, now let's see if we can make some adjustments here. If I make the top just like the bottom differentiated and stick a half there to keep it all balanced, then it's going to be half log of the bottom. So half log of k squared plus v squared plus my constant of integration. Now we need a v and an x that we can substitute in, and I've got this bit of information here. When p is at the origin, v is equal to u. So that means when it's at the origin, x is 0 and v is going to be equal to this capital letter U. So we'll substitute those in. So we'll have 0 is equal to a half log k squared plus u squared plus c. So that means my constant, I get c is equal to negative a half log k squared plus u squared. So my full expression is going to be, and what I'll do, I'll change this negative x to a positive x. X is equal to, that means everything on the other side is going to change sign. So my constant of integration now becomes plus a half k squared plus u squared, and then this part here will become minus a half natural log k squared plus v squared. Now we can put these terms together, the log terms together, tidy it up. So half is a factor, and then we'll have the log of, and because we're subtracting, it will be k squared plus big U squared divided by k squared plus v squared. And we want to find the distance OA. So what happens at A? It says it comes to rest. Particle comes to rest at point A. So we'll just write down at A, v is equal to 0 because it comes to rest. So all we need to do is now put 0 into our expression. So it's half log k squared plus u squared, and then this is just going to be 0, so we're just left with k squared at the bottom there. So that represents the distance OA. Okay, let's move on to part B. We need to work out the time it takes for P to travel from O to A. So since this is a part of the question that involves time, and we've got this acceleration that varies with velocity, we use the expression A, or the formula A equals dv dt. So A being negative k squared plus v squared is equal to dv dt. This is going to be separating variables again. So we'll leave the negative and the 1 on the left hand side, and that'll be dt, and then on the other side we'll be integrating 1 over k squared plus v squared dv. Now I reckon this is the part where you may get stuck, because this may not necessarily be an obvious one, but from the Core 2 book we have this result, which is that when you integrate 1 over a constant squared plus x squared with respect to x, it's 1 over a arctan x over a. Now I think it's also used in Pure 2, so I think because it's arctan, not arctanch, this is used in Pure 2, so I may be incorrect about that, but I've never really seen this question come up much in Pure 2, more in Core 2. Anyway, that's the result we're going to be using. So on the left hand side we're just going to get negative t is equal to 1 over k, so this is just using the result, arctan, and we're using v is our variable, v over k is like our a, plus our constant of integration. Now we want to find our constant of integration, so we need a value of t and v that we can put together, and that's going to be here. When t is 0, there it is, v is u, so we'll substitute those in. So t is 0, v is equal to big U, so that will give us negative 0 is equal to 1 over k arctan v, which is big U, over k, plus c. That means that c is equal to negative 1 over k arctan big U over k. So my full expression for x, or t, sorry, or negative t, and again like the previous one, what I'm going to do is bring the negative t over to the other side, so then that will become a positive constant, 1 over k arctan u over k, and then this part here becomes negative, so minus 1 over k arctan v over k. So we can use this now to find the time it takes to travel from O to A. Now it says at the point A it comes to rest, which means that v is equal to 0. So we substitute v is equal to 0. So that t is equal to 1 over k arctan u over k minus 1 over k arctan 0 over k. Now arctan 0 is 0, tan inverse of 0, because that's what 0 over k is equal to 0. So our final answer is the time is equal to this expression here, 1 over k arctan u over k. So not a numerical answer in sight in this question, all algebraic. Okay, there we go. So you should now be able to do exercise 4C on pages 165 to 166.